Hi everyone. Today let's talk about light. Light is an electromagnetic wave. Okay, there's a lot going on there. Let's focus first on wave. So what we know about waves are that waves have speed, and you can calculate that speed if you know the wave's frequency and its wavelength, and you multiply them together. And we can sometimes label frequency with the Greek letter nu and the wavelength with the Greek letter lambda. Well, don't get too confused by the Greek letters, but just take those values of frequency and wavelength, multiply them together, and you get the wave speed. And the speed of light is known. It's symbolized with the letter c. The speed of light is equal to about 300 million meters per second. Let's review a little bit about wavelength and frequency by looking at the electromagnetic spectrum. And if you look at the middle over here, you can see this wave with changing wavelengths and frequency. And on the right-hand side, you see the wave moving really, really fast. So there's a lot of frequency. The frequency, rather, is really high. And the space, the distance between each wave crest, is the wavelength, and it's really small. And if we go to the left, the wave gets really long. That's a big wavelength. And now it's not vibrating so fast. The frequency is low. So wavelength and frequency are opposites. Okay, let's go back to the definition of light as an electromagnetic wave. So it's got wave properties, frequency and wavelength, but it's also electromagnetic. And what we mean by that is that light acts like a wave that's both electronic and magnetic. So what do we know about electricity? Like charges repel, opposite charges attract. There's forces going on associated with electric fields. And what do we know about magnetic fields? Well, they too can also produce forces on charged objects. So, as light passes through our environment, it interacts with all the atoms. You know, atoms make up everything in the world, everything that consists of matter. And light can cause the electrons to start moving, to vibrate. And the protons, they also move a little bit. But remember, the protons are 2,000 times heavier than the electrons. So what really moves in the presence of light are the electrons. And as a consequence, when light passes through something like glass or through the air or through water, it turns out that light appears to slow down. Let's take a closer look at that. Okay, light slows down when traveling through matter. Well, that's sort of like the overall picture. It turns out that the speed of light is constant. It's always roughly 300 million meters per second. However, to us as we observe light, it appears that it can slow down when it goes through certain materials. So what's happening there? How can we say that light's always going the same speed, but then when we look at light passing through water or glass, it looks like it's slowing down? So here's the theory. Over here on the left, we got this little light ray, a vibrating wave consisting of electric and magnetic fields, and it strikes an atom of glass. And that atom of glass has electrons, and the electrons absorb that energy of the light ray and start vibrating faster, start moving faster, and the energy of the light is absorbed by the electron just briefly. So we got a little gulp as the light ray is absorbed by some of the electrons, or one electron in that first atom, and then the electron can kick out that extra energy and light reappears. And as light reappears, it travels again at the speed of light, 300 million meters per second. And it strikes the next atom, and that second atom gobbles up the light ray, and right now there's no light. It's stored in a sense in the electron's energy, and there's a delay until it burps it out again. And the light ray reappears and again travels at that same speed, 300 million meters per second, and strikes the next atom, and so on. And so it's repeatedly absorbed by electrons and re-emitted as it passes through matter. And every time it's being absorbed, there's a delay before it gets re-emitted. And so overall, it appears as though the light is slowing down as it goes through matter. So as a consequence of light slowing down as it passes through matter, we see something called refraction. So here's a straw, a drinking straw, and a glass of water, And it looks like the straw has been broken here and bent here. So what's going on there? Well, because the speed of light apparently is slowing down as it passes through different materials, right? The atoms are absorbing, re-emitting the light ray, and you have different atoms that make up glass, then in water, and then in air. The speed of light is slowing down to different amounts depending on what material it's passing through. And the net effect is we see the light being bent or disconnected here. One way to understand refraction is to look over here on the right where you have two wheels connected by an axle, and it's this axle wheel assembly is driving on a sidewalk, and as it strikes a grassy surface, the wheel on the left hits the grass first, and because there's more friction, it slows down. But the wheel on the right is still driving on the smooth sidewalk, less friction, and so it keeps going its original speed. And so as the left tire slows down, the right tire speed, keeps up the same speed. It goes a little bit faster than the left tire, and it turns. And that's sort of the same thing that's happening with refraction. As a light ray comes in at an angle, maybe it's passing through air on the left here, fast, medium, and then it strikes some water. Well, some of the light that's closest to that boundary of the water, it's going to bend first. Or not bend first. It's going to slow down. And the other light rays are just going to keep going at the same speed, but effectively faster than the light that's beginning to enter the water. And by the time the rest of the light rays enter the water, the light ray has turned or has been bent. Here are two terms we need to be aware of. Transparent means that light passes through it. It means that those atoms are not absorbing the light completely. So even though the atoms briefly absorb it, they re-emit it. However, opaque materials contain atoms that absorb the light and don't emit it, or they change it, usually into a different wavelength corresponding to heat, like infrared light. And so the light gets absorbed, at least the visible light that you and I can see, that light gets absorbed and doesn't come back out as visible light. So those materials appear dark. They're absorbing the light ray. What about color? Well, it turns out that energy is proportional to frequency, right? So as the waves vibrate more quickly, they carry more energy. There's more vibrations per second. Turns out that our eyes can detect that difference in energy. And our brains can decipher those different frequencies, different energies, as color. We perceive different energies of light as color. And then when our eyes get overwhelmed with a whole bunch of different wavelengths of light, different frequencies of light, our brain says, okay, all those different colors just sum up to white light. And that's the image that we get in our brain. So finally, if we go back to the complete electromagnetic spectrum, wavelengths that we can see correspond to be between 700 nanometers to 400 nanometers. And a nanometer is 10 to the minus 9 meters, so pretty short. And within this range, our eyes can actually tell the difference between the different frequencies, which means the same thing as the different energies. And so low energy light, slower vibrating frequencies of light appear red, and the higher energy ones, the ones that vibrate faster, are the blues and the purples. Okay, that's all for now. I'll see you in class.